This is the first of a video series which is intended to give you a quick introduction to linear algebra. My goal is to cover some of the important topics of linear algebra in 5 hours or less, so we'll see how we do. This video is part 1.1 and it covers systems of linear equations and Gaussian elimination. In particular, we will look at Gaussian elimination, we will look at the use of matrices to represent systems of equations, we'll look at solutions of systems of equations, and then we'll look at homogeneous systems of equations. The rest of part 1 is in a separate video where we look at matrix operations and linear independence. There are many topics not covered in part 1 that are important, and in particular, there are many theorems and corollaries that we don't talk about. I don't talk about transpose of a matrix, singular and non-singular matrices, or matrix inverses. And one thing I'm going to say, this first video, 1.1, it's a pretty easy video. It's not conceptually difficult, a lot of arithmetic. And actually, the arithmetic is the hardest part. But linear algebra as a course, and my video series in particular, does pick up really quickly, and you'll notice that by the time you get to linear independence. Much more conceptual, lots of things to kind of put together. We will start with the definition of a linear equation. So an equation is linear when each term has degree 1 in each of its variables. And term, if you recall, those are the things separated by pluses and minus signs. So here we have two terms in this equation, and then on this side of the equation, and one term on the other side of the equation. So this is linear because our x1 and our x2 are our two variables. And again, there's no, each term has degree of 1. There's nothing squared or anything else. Here we have a second equation. We have two variables. Actually, we have three variables, x1, x2, and x4. But you can see this term here, since the x1 is multiplied by another variable, x2, this is not degree 1. So this equation here is not linear. Here we have another equation. And again, there's two terms on this side, one term on this side. And because we have this x to the minus 1, so this degree of this variable is minus 1. It's not equal to 1. So this is not linear. Plus we have the sign. So the sign kind of messes things up too. It is not a linear equation for those two reasons. And then last, we have one more equation. There are two terms on this side of the equation, one term on this side of the equation. And because of this 1/2, this equation also is not linear because the degree of this variable is 1/2. And here I have a system of linear equations, and you can see here I have three terms. Each term has variables of degree 1. And here's a second linear equation. And together, if we want to solve this, if we want a solution for x1, x2, x3 that satisfies both of these equations, we have a system of two linear equations. So it is considered an m by n system of linear equations. M is the number of linear equations, n is the number of unknowns. In this case, we have two equations, three unknowns, the three unknowns being x1, x2, x3. Also m by n, you want to remember it's always rows then columns. So m rows, n columns. So 2 rows, 3 columns. Again, this is 2 by 3, 3 columns here. And you probably recall working with systems of linear equations maybe in middle school, and you would manipulate these equations so that you could get an equivalent system of linear equations. And by equivalent, I mean that the resulting system had the same set of solutions as the original. And the things that you are allowed to do to get an equivalent system, in other words, a system with the same solutions, are what we call elementary row operations, and there are 3 of them. The first one is you can interchange the order of the equations. In other words, you can make this the first equation and this the second equation, and of course, it won't change the solutions, x1, x2, and x3 for the system of equations. Second, you can multiply an equation by a non-zero scalar. So in other words, you can multiply this entire first equation by 2, and you get 4x1 minus 2x2 minus 6x3 minus minus 2, and you will not have changed the solution. You'll have an equivalent set. And then last, you can add a constant multiple of one equation to another. So for example, I could add this top equation to the second equation. I can also multiply it by 2 and add it, but it's more productive in this case if I multiply the top equation by 1 and add together. So my top equation remains the same, but my second equation, adding these two together, I get 0. Here I have minus x2 plus 2x2, so that will give me a positive x2, and here I'll have 2x3. Adding these together, I get 2. Also, another notation that I want to make you familiar with and also encourage you to use when you add different equations together, it's good to note what it is that you're adding. So here I'm adding row 2 to row 1, or equation 2 to equation 1. If I had added row 2 to 2 times row 1, I would have put R2 plus 2R1. The other thing is I put the R2 first, since that is the equation I will be replacing. So this convention is kind of nice in case you have a lot of manipulations you need to do. It's nice to know, to give yourself a hint of what you were doing when you go step by step. What we will end up doing is solving the system of linear equations using elementary row operations. In particular, we're going to use those elementary row operations in an orderly way called the Gaussian Elimination method. And this is an orderly manner of doing it to make sure that you're progressing. Step 1, if necessary, interchange the first equation with another so that x1 appears in the first equation. So that means x1 being your first variable, the one that's the most to the most leftmost variable is in the first equation. Step 2, eliminate x1 from every equation but the first by adding the appropriate multiple of the first equation. We did that here. We eliminated x1 from the second equation, from every equation but the first, by adding the appropriate multiple of the first equation. In this case, the multiple was just 1. Step 3, temporarily ignoring the first equation, view the remaining equations as a system of m minus 1 equations in the unknowns x2 to xn, and repeat the procedure until you have this triangular form. In this case, we can stop because if we ignore the first equation, then all we have is the second equation, and there's nothing to eliminate from the third equation. The triangular form will become more obvious as we work with more equations as opposed to just 2 equations. Let's do an example. We will look at the system of equations that we have up here, the 2x1 minus x2 minus 3x3 equals minus 1, and the second equation, minus 2x1 plus 2x2 plus 5x3 equals 3. We start, if necessary, by interchanging the first equation with another so that x1 appears in the first equation. Well, here the first equation has an x1. It's not a 0 or it's not absent. x1 is in the first equation, so we don't need to do any interchanging. Step 2, eliminate x1 from every equation but the first by adding the appropriate multiple of the first equation. So that's what we had done before. We want to eliminate this x1, and we can do that by just adding row 1 to row 2. So again, my notation, R2 gets replaced with R2 plus R1. And we did that before. We have 0x1 plus x2 plus 2x3 equals 2. So we've eliminated x1 from the second equation. Step 3, temporarily ignoring the first equation, we're going to view the remaining equations, there's only one, as a system of m minus 1 equations in the unknowns x2 up to xn, and repeat this procedure until you have the triangular form. In this case, there's no other equation to work with, so we're done here. Now we are done with this Gaussian elimination part. We do step 4, which isn't technically part of Gaussian elimination, but just to finish, I say we do what we call back solving, which is we go and we work backwards from our equations. We have x2 is equal to 2, subtracting x3, moving it over to this other side. So we have x2 solved for in terms of x3. Now we solve x1 in terms of x3. So x1 is equal to 1/2. We have our minus 1. We move the x2 to the other side and the 3x3 to the other side. But also now we can substitute this here, our 2 minus 2x3 for x2. So we also have x1 solved in terms of x3. So if we want a solution to the system of equations, in this case, x3 is free. We can allow it to be anything. And in general, it's good to choose a small number. In fact, you can choose 0. That would have been a very nice number to choose, because then x3 is equal to 0, x1 is equal to 1/2, and x2 is equal to 2. And you can check that solution in here. But I just chose x3 is equal to 2, and then plugging this in, then x2 is going to be equal to -2, plugging in x3 equals 2 into here, we have x1 is equal to 3/2. But again, there are other solutions. There's a different solution for each value of x3. Next, we're going to look and see how matrices can fit in. So the ideas here is the problem that we just did using our Gaussian elimination. Instead of carrying around all these variables, we could simply have a matrix that represents the coefficients that's in front of each variable. So for our first equation, that'll be the first line of our matrix. We have the coefficients 2, -1, -3. So I have 2, -1, -3. For our second equation, that'll be the second row of our matrix. We have the coefficients -2, 2, and 5. So here's -2, 2, and 5. So this is our coefficient matrix that goes with this system of equations. So what we consider is this matrix A times a vector x, and our vector x is going to be our variables, x1, x2, x3, will equal to our vector B, and our vector B are going to be these coefficients here, -1 and 3. So I will talk about matrix multiplication in a few slides and tell you how this multiplies out and gives you exactly the system of linear equations. But for now, I'm going to say we have this matrix here of coefficients, and then the augmented matrix is the matrix A along with the vector B. So here is our augmented matrix. So looking at how we can use this, going back to the point of solving this system of linear equations, I take my augmented matrix and I can do the same row operations. So again, if necessary, interchange the first equation with the second so that x1 appears in the first equation. In other words, that there's a coefficient here, that it's not 0 in the first row. So there's no 0 in the first row, so we can continue. Eliminate this x1, in other words, make this 0 from every equation but the first row by adding by adding the appropriate multiple of the first. So I want to get rid of this coefficient here. So I can do that by adding row 1 to row 2. So I have, again, using the same notation, I'm going to replace R2, and that's why I write R2 first, with R2 plus R1. So R1 stays the same, and then I add these two rows together. So 2 minus 2 is 0, -1 plus 2 is 1, -3 plus 5 is 2, and -1 plus 3 is 2. And then I'm done because, the same thing. I could ignore the first equation, repeat the procedure, but here there's no other row to work with. So I'm done. And when I do my back solving, I do often write my variables. The first column is for x1, the second column is for x2, the third column is for x3, so I can go on with my back solving. And here I start with my back solving. I have 0x1, so that's just 0, plus x2 plus 2x3 is equal to 2, which is the same thing that I had here. And then I have my 2x1 minus x2 minus x3 is equal to -1, which is the same equation I have here, except I divide it out by my 2. So we get the same solution. So again, we can think of using doing the system of linear equations, and just instead of carrying around all the variables, we can work with just the augmented matrix here, which takes the coefficients and then takes this B vector here. This is your first kind of application, solving a system of equations that you have in linear algebra. It's a really nice, gentle introduction into the subject, and it's something you can always come back to if you want to know, does it make sense to do something with these matrices? You can come back and say, well, does it make sense to do it in a system of linear equations? It's kind of a very solid example that you can always come back to later, which is nice. But I will warn you that sometimes students see this example and think that the whole class is going to be this simple, and it totally isn't. You'll see by the end of this video, because it's kind of a very quick summary video, that things pick up really fast. So you want to keep this example in the back of your head because it's very familiar to you and it should be able to ground you. But just know that this is really just the very, very start of this class. Things very quickly get more conceptual and pick up really fast. I should mention what echelon form is, since the last thing here was about triangular form. Echelon form is another way of saying the triangular form, and also called upper right-hand side staircase triangle. So if you have a matrix that looks like this here I did a 4x4, it's where you have along the diagonal, everything on the diagonal and above can be 0 or non-zero, but everything below is 0, and it's kind of like the staircase look, that all of these things are 0. So that is your goal when you're doing this Gaussian elimination, and is this triangular form. And you can see here you have this triangular form. And here is the technical description of what it is to be triangular form. All rows that consist entirely of zeros are grouped together at the bottom of the matrix. So here we don't have any rows entirely of zeros, but if you had rows of entirely of zeros, they'd be at the bottom. The first, counting from left to right, non-zero entry in the I+1 first row must appear in a column to the right of the first non-zero entry in the ith row. So in other words, if this is our ith row, then the next row, the first non-zero entry has to appear after the first non-entry in the row above. That's all this is saying. And again, the effect is you get this staircase look. We will do one more example. We have the system of linear equations, x1 plus 2x2 plus x3 minus x4 equals 1. x1 plus 2x2 minus x3 plus x4 equals 5. And minus x1 plus x2 plus 2x3 equals 0. So I write my coefficient, my augmented matrix. So my coefficients are 1, 2, 1, negative 1. So here I have 1, 2, 1, negative 1, and then I have 1 for my b. For my second row, I have 1, 2, negative 1, 1, 1, 2, negative 1, 1, and then I have my 5 as my second. And then for my last row, I have negative 1, 1, 2, 0. So negative 1, 1, 2, 0, and then I have 0 over here. And now I can do my row operations. So I don't need to interchange the rows because my x1 appears in the first equation. In other words, there's not a 0 over here in this position. So I'm going to eliminate x1 for every equation but the first. So I need zeros in every equation but the first. Also, you can think of, I'm trying to get my triangular form. So first, I'm going to come over here and focus on making these coefficients equal to 0. So I can do that. I can replace R2 with R2 minus R1. So here I have, oh, by the way, here I have R1. Then R2 is going to be R2 minus R1. So 1 minus 1 is 0. 2 minus 2 is 0. Minus 1 is negative 2. 1 minus 1 is 2. And 5 minus 1 is 4. Now I need to eliminate x1 from this last equation, the third equation. So I'm going to replace R3 with R3 plus R1, and this is what I get here. And now the next step is to ignore the first equation. So I'm going to ignore this first equation, which is why I blocked off this line here. And I'm going to view the remaining equations as a system of m minus 1. Remember, that's the number of rows. Again, since I've eliminated one row, I have one less row. And I also want to eliminate one of my unknowns, the x1, so that I'm only looking at x2 through xn. So essentially, I'm eliminating this column, this row, and I'm looking now at just this matrix, and I'm going to start my procedure over again. So step 1, if necessary, interchange the first equation with another so that x1, now this is my x1, appears in the first equation, but x1 doesn't appear in the first equation because it's multiplied by 0. So I need to interchange these two rows. And I notate that with this if and only if sign. So interchanging row 2 and R3 is this if and only if, and that's what I have done here. The second step, eliminate x1, that's this first variable here, from every equation but the first by adding the appropriate multiple of the first equation. So here I want to eliminate x1 from the next equation, but you can see it's already eliminated because there's a 0, so I'm done here. And then I can ignore the first equation, but then I'm only left with one equation. So I'm kind of done doing this Gaussian elimination. From there, I'm ready to do back solving. So my first equation is x1 plus 2x2 plus x3 minus x4 equals 1. I have my 3x2 plus 3x3 minus x4 equals 1. And then last I have my 2x3 plus 2x4 equals 4. And sometimes, just a tip, because sometimes it's hard to read everything off this matrix, sometimes I write the variables underneath just to make sure I'm lining everything up and not making some stupid mistake that then takes hours to trace back to figure out what's going on. So here I have that x3 is dependent on x4, and x4 is free. So, right, because I don't have 4 equations, 4 unknowns. I only have 3 equations, 4 unknowns, which is why I have one variable that is undetermined or can be free, and I generally choose the last variable to be free. Then you can solve x3 in terms of x4, you can solve x2 in terms of x4, and x1 in terms of x4. And this is my solution. And just to check, to make sure you're going in the right direction, you can just set x4 equal to 0, and then plug in to see what you get for x3, x2, and x1. Put that back into your equation, your system of equations, and make sure that this is actually a solution. If these numbers work, it isn't a guarantee that these formulas are right. You might have just gotten incredibly lucky, but it is a sanity check to give you kind of a little warm, fuzzy feeling that maybe things are going well for you. One thing about this work, this part of the course, you can double check a lot of your work, and actually everything in this video has stuff that allows you to double check your work. So now that we've covered Gaussian elimination and looked at how we can use matrices to represent these systems of linear equations, we're going to talk about the solutions of systems of equations. What are the possibilities for solutions? And the answer is a system of linear equations can have infinitely many solutions, it can have no solution, or it can have unique solution. There's no such thing as having 2 solutions or 3 solutions. It either has infinitely many, no solution, or unique solution. And we can see that when we only have a system of 2 equations. That's the easiest way to see that, because when we have 2 equations, 2 unknowns, those are 2 lines, right? 2 linear equations are 2 lines. So if we have 2 linear equations, when we have 2 lines, either the 2 lines, the 2 equations, really represent the same line, in which case you have infinitely many solutions. In other words, every possible value of x1, x2 will satisfy your system of linear equations, so you have an infinite number of solutions. Or your 2 lines can be parallel, in which case they never intersect, and there's no x1 and x2 they have in common, so there's no solution. And last, it's possible that your 2 solutions intersect at one point, in which case that one point is where your x1 and x2 works for both equations. So you have a unique solution. So again, for any system of linear equations, there are only 3 possibilities: infinitely many solutions, no solution, unique solution. And to remember that, you might want to remember these 3 drawings of 2 equations, 2 unknowns. Our first example is of unique solution, and this is where we have the same number of equations as unknowns. So x1 plus 2x2 is equal to -5 is our first equation. 2x1 minus x2 is equal to 5 is our second equation. So our augmented matrix is 1, 2, -5, 2, -1, 5. I do my row reduction, I do my back solving, and I get this unique solution: x1 equals 1, x2 is equal to -3. And you can plug these values back in and verify it is a solution. Next, we have an example of infinitely many solutions. So the first equation is x1 minus x2 minus x3 equals -2. The second equation is 2x1 plus x2, plus 3x3 equals 1. And the last equation is minus 3x1 plus x2 minus 2x3 equals 1. So our augmented matrix is 1, negative 2, 1, negative 2, 2, 1, 3, 1, negative 3, 1, negative 2, 1. And you can see I do my row operations until I get this triangular form. And just to make things a little more easy on myself later for algebra, because I'm really bad at algebra and arithmetic, I went ahead and divided this row by 1/5. So now I have the coefficient for x2 is 1x2, 1x3 is equal to 1. So this is my equation here. So I get x2 is equal to 1 minus x3. Then I have 1x1 minus 2x2 plus x3 is equal to negative 2. So reading off my coefficients is equal to 2. That's this equation here. Solving, plugging in x2 is equal to this in terms of x3. I get x1 is equal to minus x3. So I can choose a solution for x3. So I'll just choose 1. It's a small number. And you could have chosen 0. Maybe that's even a better way to do this. But I chose 1. And then I get x2 is equal to, where's my x2? x2 is equal to 1 minus x3, so x2 is 0, and x1 is going to be minus 1. And if I plug that in, you can see that it is that x1 is equal to minus 1, x2 equals 0, and x3 equals 1 is a solution to the system of equation. And I could have chosen x3 equals 0, as I said, or x3 equals 2, x3 equals 1 million. So for every choice of x3, there is a solution. You can solve for x2 and x1, and that will solve the system of equations, which means there are infinitely many solutions. Last, we have an overdetermined systems. In other words, more constraints, more equations than unknowns. So here we have 3 equations and only 2 unknowns. Here's my augmented matrix. I do the row reduction, and then I do my backwards solving. And what you see is I have 2x2 is equal to minus 2, which suggests that x2 should be equal to minus 1. But I also have that 3x2 is equal to 0. So there's no value for x2 that will satisfy these 2 conditions. So it's basically, since no x2 satisfies these 2 conditions, there's no solution to this system. The system is inconsistent, it's overdetermined, and has no solution. One more example, which is a little bit bigger. We have the system of equations 2x1 minus 3x2 plus x3 minus 3x4 plus 2x5 equals 6. The second equation, 2x1 minus 3x2 plus 5x3 minus x4 plus x5 equals 8. The third equation, 4x3 plus 3x4 plus 2x5 equals 3. And the last equation, minus 2x1 plus 3x2 plus 3x3 plus 3x4 minus 9x5 is equal to negative 6. So the augmented matrix is 2, minus 3, 1, minus 3, 2, 6. The second row is 2, minus 3, 5, minus 1, 1, 8. The third row is 0, 0, 4, 3, 2, 3. And the last row is negative 2, 3, 3, 3, negative 9, 6. It row reduces to this echelon matrix here. You can do your backwards solving, and you see x5 is free. You can solve x4 in terms of x5, solve x3 in terms of x5 as well. And then you'll get your next equation, you'll need another free variable. So x2 will become free, and x1 can be solved in terms of x2 and x5. And one of the points of this equation, this system of equations, is the number of unknowns. If you have more unknowns than equations, then you're going to have free variables. And the number of free variables you have is going to be the number of unknowns minus the non-zero rows. So in this case, you have how many unknowns? You have 5 unknowns. You have 1, 2, 3 non-zero rows after you've done your echelon, once you're in echelon form. So you expect 2 free variables. And once you have free variables, then you have infinitely many solutions. Now that we've looked at the possibilities for solutions of systems of equations, and remember, there are only 3 possibilities: no solution, a unique solution, or infinitely many solutions. We can do our last topic for this video, which is homogeneous systems of equations. So the homogeneous system is when our b vector, this vector here on the other side of the equal sign, is all equal to 0. So if this vector here again is all equal to 0, it's homogeneous. And one thing to know, the first thing to know about the homogeneous system is there's always a solution. It's always consistent because you can make x1, x2, x3, and x4 all equal to 0. So there's always what we call this trivial solution, the trivial solution being the 0 solution. So since there's always at least one solution, it's never the case that there's no solution. So the other possibility is there are infinitely many solutions. Remember, there's 3 possibilities. No solution, but we know there's at least one unique solution, so it might be a unique solution, or it might be infinitely many solutions. So let's look at the 2 possibilities of unique solution or infinitely many solutions. So here's our first example. I have x1 plus 2x2 plus x3 plus 3x4 equals 0. Our next equation is 2x1 plus 4x2 plus 3x3 plus x4 equals 0. And our last equation is 3x1 plus 6x2 plus 6x3 plus 2x4 equals 0. The augmented matrix is 1, 2, 1, 3, 0. The next row is 2, 4, 3, 1, 0. And the last row is 3, 6, 6, 2, 0. And it is row equivalent to this matrix here, 1, 2, 1, 3, 0, 0, 0, 1, negative 5, 0, and 0, 0, 0, 8, 0. So I do my backward substitution, and I get x4 equals 0, x3 equals 0, and x1 is equal to minus 2x2. Since I have this free variable, that means there are infinitely many solutions, because every time I plug in a value for x2, I get another solution, and there are infinitely ways I can plug in for x2. So here is a homogeneous system of equations that has infinitely many solutions. Also remember, we were expecting free variables because the number of free variables is equal to the number of unknowns. In this case, there are 4 variables or 4 unknowns, minus number of non-zero rows. Here, of course, when I say non-zero rows, we're talking about once you get it in echelon form. And there are 3 rows that are non-zero. So we're expecting 4 minus 3 is equal to 1 free variable. Our second example is a system of equations starting with 2x1 plus 3x2 minus x3 equals 0, minus 2x1 minus 2x2 plus 3x3 equals 0, and finally 2x1 plus 6x2 plus 9x3 equals 0. Our augmented matrix is 2, 3, minus 1, 0, minus 2, minus 2, 3, 0, and 2, 6, 9, 0, which is row equivalent to 2, 3, minus 1, 0, 0, 1, 2, 0, 0, 0, 4, 0. When we back solve, here we get x3 equals 0, and then we have x2 plus, x3, which is 0, is equal to 0, so x2 has to equal 0. And then finally here we have something, 3 times x2, which is 0, and a minus 1 times x3, which is 0. So we have 2x1 equals 0, so x1 equals 0. So x1, x2, and x3 equals 0, so we have only the trivial solution. And remember, the trivial solution is the 0 solution. So it's a unique solution, one solution. So these special cases for homogeneous systems, it's important to remember them because we're going to be looking at these all the time when we talk about linear independence. As I had mentioned before, this video is a pretty easy introduction to linear algebra, and it does have some very useful examples, like the system of linear equations is your first kind of application of linear algebra, and it's a nice basic system to get started with, and you can always go back and kind of refer to these type of system of equations as sort of an example. But linear algebra as a class, and also in my videos, will pick up pretty quickly, so you'll notice that in the next video. I hope you'll watch that as well, and in the meantime, thank you for watching.